What does it mean to be measurable? Well, in this lecture, we're going to go beyond the basic idea of measurability for sets. We're going to talk about measurability for functions. That is, if we have one measure space, and we have another measure space, and we have a function mapping from one to the other, what does it mean for that function to be measurable? We're going to need this definition because it's going to be critical for our study of the integral. Let's look at these measurable functions now. Back to another lecture of Statistics 571, Probability and Measure. Today we'll be starting Chapter 2 of my lecture notes. The topic is functions, random variables, and the integral, because measure theory was really geared around this idea of how can we integrate a more general class of functions beyond what is Riemann integrable. Right? If we go back to Riemann, that would have been in the 19th century, but again, we're in the 20th century now, technically 21st, but in this course, we're in the 20th century, and we want to do integrals like a good 20th century mathematician, but we're not going to get there quite today. Today, what we need to talk about are, measurable functions, which are going to be the functions that we're going to be, considering in this course. Before we do that, we're also going to talk about simple functions and then use those to build up to measurable functions. And then in the next two lectures, we'll be talking about lots of topics in the theory of integration. So let's go check that out. So the first thing I'd like to talk about is the idea of a simple function, or because this is probability and measure class, a simple random variable. Random variables are one of those things that it's like you think you know what it is until you really stop and think about it, and then you're like, well, wait, what exactly is what's a normal random variable anyway? It just takes values in the normal distribution? Like, what's going on here? We're going to give more context to that and show that in this case, the random variable is basically going to be a measurable function mapping from a probability space into the, omega into the reals. But we'll make that a little bit more precise now, besides me just rambling about it. And in fact, why don't we start with the idea of a simple random variable? So what we'll say is let omega f, the sigma field, and in this case, instead of using mu, I'm going to use p for probability, be a probability space. So recall, right, a probability space is just a measure space, but now I have a probability measure, which means, i.e., p of omega is equal to 1. Omega is kind of like the event space, right? Something has to happen with probability 1. So omega is the everything, and something within the context of everything has to happen. Anyway, what we're interested in is the idea of a random variable. So what we're going to start with is the idea of a simple random variable. Variable x. And x is going to actually be a function that's going to map from omega into the reals. I think in this case, we can take positive or negative. Sometimes we'll need non-negative random variables to make things a little bit easier, but in this case, we think of it as a function. Now, just to try to be a little bit clear, how is this different than what we learned about with a measure? Right? Recall that a measure, mu, is a function from the sigma field into the positive or non-negative reals. So it's slightly different, right? X is going to take any point in omega and assign a value to it. A measure is going to, in some sense, measure a set where F is the sigma field of subsets of omega. So it's a little bit different. Well, it's actually a lot different, but it's just good to kind of see these side by side to see what's happening here, I think. Well, nevertheless, right, we're calling this a simple random variable. So what does that mean? Well, that means the simpleness of it implies that x omega only takes a finite number of values, which we'll denote as x1, little x1 through little x, which notation would p. Trying to keep with the notation I was using. So the simpleness of it just basically says that it only takes on a finite number of values. You can think of this kind of like a step function, and I'll give an example a little bit later. But moreover, when does it take these values? We want to say also the set, the collection of omega in big omega such that x of omega is equal to x I, say, for just whatever I from 1 to p, is going to be an element of the sigma field. So we want to make sure that the sets where x takes on one of these values, one of these values, or I guess each of these values, the sets where each of these values occur is going to be an element of our sigma field, and thus something that we can measure, we can assign a probability measure to. We can basically ask, what is P of, right? The whole point is that I can take this and I can wrap it in a P and ask, well, what's the probability measure of this set? I'm going to delete that there. But that's the idea. Now, moreover, we can actually write this out as an equation. So let's say A1 or AI, I from 1 to P, AI in F, be a disjoint partition of omega. So what I mean by that is that if we take the union, I'll just write it out to be clear, right? What I mean by that is that if we take the union I from 1 to P of the AIs, we get omega, and furthermore, AI intersect AJ is going to be the empty set if I is not J, of course. So that's what I mean. We just take omega, we cut it into P pieces with our, I guess, cutting knife, and what we can do is we can assign x to take the value little x I in for omega that live in AI, and we can write that out much more clearly than I can speak it out, right, as x omega being the sum I from 1 to P of little xi, a real value, times the indicator function that omega is in AI. So again, if in this case omega is just the real number line, right, then AI could just be intervals, for example, that cover this line in such a way, and then x would just take on values at those different points. Right, so yeah, then we can also, the point of all this is that we can then say that the probability that x is equal to little xi is, well, we write that notationally as p of x is equal to little xi, right? This is in some sense, a shorthand notation that's hiding everything behind the scenes, but it's something that you would see in like a intro probability class, right? If you're doing like binomial probabilities, right? If x is a binomial random variable and little x is some value, then what's the probability that you get that? But what's really happening behind the scenes is we're really saying, what is the measure of the set of omega, little omega, in big omega, such that x omega is equal to little xi. And this, using the fact that I defined that to be A, is just the probability measure of AI. So this is, in some sense, what's happening with a random variable. A random variable is, well, as someone told me once, a random variable is not random. It's actually a measurable function, right? It's a function from some measure space into the reals. Or I guess it could be into other spaces as well, but we'll just, for now, treat it as mapping into the reals. Of course, you could have like bivariate random variables. You could have random functions. You could have lots of random stuff. But this is kind of the idea. And with this notation, we can, I'll say, we can also define the expectation of x to be, well, ex, which in this case we define it, right? This is, in some sense, we don't, in this course we don't know what expectation is yet, right? It's an integral, of course, but we don't even know what an integral is in this course yet. So we're just going to say ex is, for a simple random variable, is going to be the sum I from 1 to p of little xi, the value it takes, and then p of x equal to little xi. So again, what we're basically saying is, if I want its expectation, what I can do is I can say, well, in this set, with a certain measure, it takes on the value of x1. In this other set, it takes on the value of x2. And then add those all up, weight by the respective probability measures. And there's your expectation for a simple random variable. And of course, this is like the basic setting. We want to turn this into something that we can take an integral of for a general measurable function. Just to give an example, before we talk about a simple measurable function, what we could do is we could consider omega to just be, let's say, the standard unit interval. We can say half open, half closed. Eventually we can just say it's, the closed unit interval or whatever, but we'll just stick with it like this to keep with what we were doing with Lebesgue measure. And then we could define, let's say, A1 to be, actually, you know what? Maybe I'll just draw a picture. I kind of like that better. So if we have 0, 1/4, 1/2, 3/4, and we'll say 1. Right? Then what we can do is we can define, let's say, the set A1, A2, A3, and A4, where, okay, 1/2 is the left side's going to be open and the right side's going to be closed, so that we have a disjoint partition of this. But the idea that I'm trying to get at is that we could assign values xi to be I minus 1 divided by 4, which in this case, if we consider the, I guess, vertical axis, 0, let's make sure I have enough room here, 1/4, 1/2, 3/4, and 1, then I have a function that's going to look like, well, it's going to take 0 for the first interval, then it's going to take a value of 1/4 for the second interval, then it's going to take a value of, I guess, 1/2 for the third interval, and a value of 3/4 for the fourth interval. And if we consider the fact that if we draw the diagonal line x equals y in here, we would get something that looks like this. So this would be a simple function. We can compute its expectation, which, you can fill in the steps yourself, but if we compute the expected value of this thing, if I did it correctly, we should get 0.375. This is basically a discrete approximation to the uniform distribution on the unit interval, right? If I were to take this same setup, but instead of cutting the interval into 4 pieces, what about 8? What about 16 or 32 or 64, right? I can keep cutting this up, and I'll get a closer and closer approximation to this diagonal blue line I drew there. The diagonal blue line is not a simple it's not a simple random variable. It would just be a, I guess, measurable random variable. So these are things I'm getting ahead of myself, of course, but I want to illustrate this to kind of motivate where we're going, right? We have these green lines, and we want to turn them in some sense to the blue line so we could define what a uniform distribution on the unit interval is in a proper measure theoretic sense. At this point, we just have simple random variables, so that's what we got to work with. But of course, all right, we're also in a mix of measure theory and probability class, so we could also just ask, well, what about just a simple measurable function? I feel like measurable, I never spell it right. Okay, there is no E. I inconsistently will spell it with an E and without an E, because when I do math, I can't actually spell. It's like mutually exclusive within my brain. So I apologize for all the spelling mistakes that are probably all throughout this. Anyway, simple measurable function. This is in some sense the exact same thing we talked about before with a simple random variable, except that now we have let omega f mu be a measure space. In this case, right, it could be finite. It doesn't have to have a value, like mu of omega doesn't have to be 1. It also doesn't have to be finite. It could be finite. It could be sigma finite. It could probably, I'm sure we could also define this in the case that it's just a general measure as well. Oftentimes we want things to be sigma finite because otherwise it gets a little bit of a headache, but I think everything should be perfectly fine even outside of the sigma finite realm. But of course, the more general you make things, right, in mathematics, then often the more nervous I become. I'm like, is everything still holding like it should? I hope it is. But it should. Nevertheless, we can say f from omega into the reals is measurable. Well, I guess we haven't defined, we're going to define what a real measure is. We'll just say is a simple measurable function is such that it can be written in the form f of omega is equal to the sum I from 1 to p of x I omega in b I, where much like the ai's, the bi's, well, I guess in this case, I should say, we actually don't need, strictly speaking, a disjoint partition. So I think in this case, I kind of skipped that. It's a little bit cleaner to write this with the ai's being a disjoint partition of omega, but in some sense, we don't really need that. We would just need the bi's in this way. I guess we would have to cover all of omega so that the domain of f is in fact all of omega. But otherwise, we could just say we have a bunch of bi's, which are in the sigma field. They're measurable in that sense. They live in the sigma field that we have to work with. And then we define that f takes a certain value if the omega happens to live in that bi. Yeah, I say here they don't need to be disjoint, but we could always define it in terms of disjoint bi to make things a little bit cleaner. I have a couple things that I'll leave for you to work out yourself, the exercises to consider. That is that if f and g, mapping omega into r, are simple functions, then so are, that is, these are also simple functions, which is f plus g, or f times g. This is not f of g, right? This is f omega times, let me just make sure that's explicitly clear. This is f omega times g omega multiplication style, as well as things like the max of f and g, and the min, yeah, of course. So what this means is that if you can write if f and g are written in this sort of step function way, as just a sum of a bunch of weighted indicators, then their summation is also, and their product and their max and their min should also be of this form. It seems pretty clear, like when you think about it, you're like, yeah, that kind of makes sense. But it is always good to just go through and make sure you can write it out, just to see if you can actually do it. Oh yeah, there's one thing I forgot that I wanted to define here. So this is exercise 1, then I'll say we define the integral of a simple function to be. So again, we don't know in this course what an integral is yet. So this is we're defining it, right? We're saying that if I have a simple function f in a measure space with measure mu, then I can define this to be the sum I from 1 to p of x little xi times the measure mu of b I, right? This is the function up here, and this is its integral down here, just to make sure it's clear that I'm using the same function I defined above. So this is how we can define an integral for a simple function, a simple measurable function, that is. And of course, we want to extend this to more interesting functions. But given that we have this idea, this definition of what an integral of a simple function is, then we have another exercise for you to try at home, which is, again, for, well, we're going to do a slightly different thing. For f and g, mapping omega into the non-negative reals, simple functions, of course, because we haven't defined anything else yet. So, so if we have two simple functions that map omega into the positive reals, or the non-negative reals, I guess, then show that the integral is a linear operator maybe functional is the right word, but a linear operation. I guess an operator is just a more general type of functional, so it doesn't really matter. But what I mean by that is that there's two things. First, we want to show that it's linear. Well, it can be broken up over a summation, right? So these are the things that we want to check. We want to show that the integral of f plus g is the integral of f plus the integral of g. And we would want to show that the integral of c times f, I haven't defined what c is, it's a scalar, is equal to c times the integral of f d mu for some c greater than 0. C is, of course, or maybe I'll say, yeah, I mean, it's a real value. It's just a number greater than 0, a scalar value. That's the word I was looking for, scalar. Some scalar c greater than 0. Everything's positive here just so we don't have to deal with the headache of having subtraction, because it's annoying and you're going to have to deal with like infinities. And we don't want infinity minus infinity. That's just going to lead to some troubles. So we're going to avoid that for the time being and just stick with positive stuff. Be positive, right? Anyway, this is going to lead into, this is kind of like the intro to this lecture. We talk about simple functions and simple random variables. Now, we want to, take it up a notch and say, well, what is a measurable function and a measurable random variable? So let's look at that. All right, so let's say the next section, what we're going to want to do is consider measurable functions and random variables. So what we want to do is we want to figure out a way to extend this idea of a simple random variable, but into a more interesting case, right? That doesn't just take on a finite number of values. So in this sense, we need two spaces. So we're going to start with, we need two what are called, not measure spaces, measurable spaces, which I'll define as, let's say bold X and script X for the first one. That is where bold X is the space and script X is the sigma field on that space. And then similarly for Y, we'll have, do I like that one better, or do I like, maybe I like that better as bold Y. Okay, we'll do bold Y and then we'll do script Y for sigma field. So a measurable space, right, is in some sense a measure space without having defined a measure yet. So we have a space, somewhere to work, right, an X, a Y, an omega, whatever, and we have a sigma field that's cutting up that space into subsets in the sigma field sense. So we could define a measure on that sigma field, but we haven't done that yet. So it's basically, like I said, it's a measure space without a measure defined on it. It's very similar actually to, I guess, a topological space where you would have a space where you're working and you would have subsets that are open, right? The open sets in that space, the topology on that space. Anyway, in this case, we have our two measurable spaces. And then what we're going to say is that, I guess we can write this out as a definition. A function f mapping x into y is said to be measurable. I guess I should define. I'm one step ahead of myself. Let's hold off for that in 1 second. I need to define what I mean when I take a function and I plug a set into it. So let's say f is just some function that maps x. That's a terrible bold X. That maps x into y. And A is a subset of X, and B is a subset, that's not subset, a subset of Y. Now, in this case, we can say that F of A is a set, right? It is all of the Y in Y, such that there exists an X in A such that f of x is equal to y. So what we're doing is we're taking the set A that lives in X and we're taking that whole set and we're mapping it into Y. Similarly, we can do this backwards. We can define the inverse. the inverse of B. Now we're taking a set from Y, and we're inverse mapping it back into X. So this is going to be all of the X in the space X such that there exists a Y in B such that the same equation holds. F of X is equal to Y. So in some sense, right, maybe I can draw this out just because it's nice to draw it out sometimes. Right, what we have, there we go. What we have here is we have our space X. And we have our space Y. And then we're going to need a set A. And we're going to need a set, well, I'll keep it in green, right? A gets mapped into some other set. It may not be connected the way I'm drawing it, but it's just easier to draw it this way, right? F is going to map A into FA. This is the F mapping. Now, similarly, we can go the other way. We could have a set B that lives in Y, and it's, I guess, the inverse image, which lies over here. This is the F inverse map. So all we're saying is we're just we're defining a new set where the points in the first set get mapped into the point in this new set, if that makes sense. Anyway, now that we have this notion of what it is to plug a set into a function, or what f of A and f inverse of B means, now we can define what it means to be measurable. So a function f mapping x into y is said to be measurable. Sometimes, to be explicitly clear, you see someone write something like measurable xy, which is it's measurable with respect to the x and y sigma fields. Oftentimes this is just ignored because you're dealing with like Borel sets on the real line, and it's just implied that you know what's going on here. But strictly speaking, we're measurable with respect to the two different sigma fields, x and y. If the sigma fields change, the measurable functions, well, the set of measurable functions may change. A function that is measurable with respect to certain sigma fields may not be measurable with respect to other sigma fields, is the point. Anyway, I haven't told you what measurable means yet. It's said to be measurable if f, we'll write down here, f inverse of B is in X for any B in Y. So what it means is that I can take an element of the Y sigma field and I can map it back, inverse map it into X. And what I get when I move into X is I get an element of the sigma field. So it's, in some sense, it means I'm mapping elements of I'm inverse mapping, I guess, elements of sigma field Y into elements of sigma field X. And that's what we mean by measurable. So yeah, it's a little bit abstract, right, when you first see it, but hopefully it'll become more familiar when you get used to working with it. So as I mentioned, very often in this course in probability theory, we'll be dealing with the real line. So often we are working with the Borel sigma field, which we could write, for example, as x and script b. Maybe we'll say script b of x to indicate that it's the Borel sigma field over the space x. Now, of course, in this case, we would have to define, like I mentioned earlier, this is very closely related to the idea of a topological space. Little side note. Note a topology. I told you, spelling and math is hard to do at the same time. A topology on X is the collection of open sets. I don't have a good notation for that. We'll just call it T, script T, which looks like a really big towel for topology. Then the sigma field constructed from this topology, this collection of open sets, is the Borel sets. So that's what I mean, is that to define the Borel sigma field, strictly speaking, we need to know what open sets are on X. So if we have the collection of open sets on X, we can define the Borel sets, or the Borel sigma field. Yeah, I said that was the first note. And then secondly, Y, basically this Y space, where we're mapping into, is often, especially in this course, going to be the reals and the Borel sets on the reals. And sometimes maybe the positive reals, just because things sometimes become easier if we ignore negative numbers. I should strictly say non-negative reals, because we'd probably include 0. Nevertheless, what we say is, in this case, we'd say that F is Borel. Let's write down the next line. Borel measurable. So these are all these terms that you might see people use in practice and be like, what in the world are they talking about? So if we just have a measurable function, it's just mapping one measurable space to another measurable space in this way that it maps back elements of the sigma field to elements of the sigma field. If the sigma field we're working with is the Borel sigma field, then very often people just say F is a Borel measurable function. And we'll say, secondly, similarly, we can replace the Borel sets. Did I say over R? Yeah, we'll say over R, with this M lambda R, which are the Lebesgue measurable sets, to get Lebesgue measurable functions. This is important because the Lebesgue measurable functions are the ones we're going to want to be taking integrals of, which is kind of the thing that we're getting to here through this first lecture discussing what measurable functions are. So we need to know what measurable functions are, and then after this we'll spend at least 2 or 3 lectures just integrating them and showing what cool things you can do with integrals. Nevertheless, that's roughly the idea. Now, oh yeah, we got lots of time. Next, what we'll be doing is, I'm just going to, in some sense, end with a long list of cool facts about measurable functions. So let's do that. Cool facts about measurable functions. Right, so let's get into it. Number 1. Well, inverse images of set functions preserve set operations. What does that mean? Let's write that out. Inverse images of set functions preserve set operations. Okay, maybe it makes a little more sense now that I wrote it out. But let's use math language to explain what I actually mean here, i.e., for a function f that maps x into y, and for a and ai subsets of y, I think in this case we'll say I in I, maybe some countable index set just to give it, something. We'll say then f inverse of the union over I in I of the AIs is going to equal the union I in I of f inverse of AI. What did I do? I switched the order of the f and the union, right? They swapped orders. It was the f inverse of the union of the AIs versus the union of f inverse of the AIs. That's, I guess, cool fact number 1A, and cool fact number 1B is that f inverse of y, the complement, which is y set minus a, is equal to x minus f inverse of a. So you can, in some sense, do unions and do, I'm blanking on the word. What is it? It's not set differences. I just said it. Whatever C stands for. Man, I'm just having a complete mental blank. Basically, you can subtract. Why in the world can I not remember that word? That is so annoying, right? AC. And you're probably watching this thinking like, well, obviously it's a complement. That's the word I was looking for. Always like a good compliment. Do compliments, right? So that's what I mean. Cool. So, you can try and prove this yourself. I'm not going to write it all out. The way you would do this typically, like in general, let's just say, if I want to show that sets A and B are equal, then show that both A is a subset of B and B is a subset of A hold. So what you would start is say, okay, I have an element of A, show that it necessarily has to be in B. And if I have an element of B, show that it necessarily has to be in A, and therefore the two sets are the same thing. You can do that up here. It's not the most interesting thing to prove, but you can write it out. It might be worth trying to write it out and just say, okay, let's let an element A be an F inverse union of the AIs. Now, does that necessarily land inside the union of F inverse of AI? My claim is yes, but you can check it if you want. These results are really important because if you think about it, we're talking about countable unions and we're talking about set subtraction, taking complements. What this means is that if we want to check if a function is measurable, we don't need to look at the entire sigma field. We just need to look at sets that generate the sigma field. So this is, I'm going to say, important. Checking whether or not F is measurable can be, what's the proper way to write this out, right? I guess what I would need is let's say, can be done for A in A, where sigma of A is equal to Y, instead of for all elements, for all sets, let's say, in Y. So maybe an example of what I mean will make this clearer, which is for example, let AT equal the half-infinite interval of this form. And this is for all t in R. Then these sets generate the Borel sigma field on R. Hence, if we have a function that maps into the reals, and we want to know if it's measurable, then what we can say is well, okay, I could check that every single Borel measurable set gets, on the real line, gets mapped back into a element of the sigma field. But that's annoying. On the other hand, we could just do it for all t, let's say, sets AT instead. And that makes it a lot more tractable, right? And these sets AT are very suggestive of the idea that we might be looking at, say, a cumulative distribution function, which says, what's the probability measure from minus infinity to some point t, right, as t gets bigger and bigger, right? That's why AT looks a lot like something you would see if you're working with the CDF. Let me write that out. That is, we can answer the question, or we can say that f is measurable as long as the sets, which is the x, such that f of x is less than or equal to t, are measurable. This is actually a pretty useful fact, so I'm going to give it a blue box. We're going to use this, I think, in 2 lectures or something. I'm pretty sure we use this, I forget, with the product measure, I believe, when we do product measure and Fubini and Tonelli's theorem with the integral. I think somewhere in there this shows up to show that things actually exist. I kind of forget, but it is going to show up again. That blue box will show up again, so stare at it for a second and burn it into your retinas, because we will need that fact again. Anyway, fact number 2 is important fact number 2, or really cool fact. What was I calling this? Cool fact. Cool fact number 2 is, well, basically not that interesting, actually, but it's still useful. For any A in the sigma field X, the indicator function indicator that X is in A is measurable. Okay, why in that case? Well, in this case, right, the sigma field generated, if we call this, let's say, f of x, generated by F inverse is simply going to have 4 elements in it. It's going to have the empty set, it's going to have A, it's going to have A complement, and it's going to have, I guess, omega or X. I guess I was calling it X. Right? And all 4 of those things are contained in the X sigma field. Because A is in there, of course, the empty set and the whole space is in there. A is in there, therefore A complement has to be in there. So that's like a pretty simple example of a measurable. It's perhaps the simplest, maybe non-trivial example of a measurable function is the indicator function for any set A that we choose. Fixed set, of course. We pick a set A from our sigma field, we get a measurable function. Cool. So we know that measurable functions at least exist, right? We have one. That's always good, right? Because every so often in math, you could start to argue about some object or some class of objects and then realize that there is no thing that exists in that class of objects. That's not the case here. We have measurable functions. I wrote one right down. Let's do some more cool facts. All right, really cool fact number 3 says that for measurable functions, f and g mapping from x into the reals, where are we? Then, well, f of x, or not f of x, x, f plus g, and f times g are both measurable. So that's a useful fact to know. This follows from a proposition in Dudley's book, but it shows up. It's better to talk about that when you can talk about product measures. So we're not going to prove that right now. We're just going to state it as a fact. We'll just say, talk about it later with product measures. So we're just going to ignore why that's true for the time being, but it does make sense. I mean, I left it the above for simple functions as an exercise, just basically saying, well, if you have 2 simple functions, then yeah, you can add them together or multiply them. You still get a simple function out. You can do the same with measurable functions. So it's, I mean, intuitively, it kind of makes sense. This next one I actually will prove, so I'm not going to just get off the hook easy and just kind of skip all the justification here. We'll say for measurable functions, fi, I from 1 to infinity. So again, I write I from 1 to infinity to indicate that we have a countable collection of measurable functions. If things are uncountable, then that again makes me a little nervous that what I'm about to say is going to, fail. But if we have a countable collection, in fact, yeah, because we have to do countable set operations. So if it's uncountable, that's probably not going to work. Even if I can't immediately come up with a counterexample off the top of my head. Anyway, if we have a countable collection of measurable functions that map from x into the reals, then we'll say the following are also measurable. And we have a couple things. Well, first we have the sup, the supremum over all I of fi, measurable function. We have the infimum over all I of fi, measurable function. We have the lim sup as, I guess, over I of fi. We have the lim inf of the fi over I, of course, everything's over I, and also just the pure limit as I goes to infinity of fi if it exists. These other things, the soups and the lim soups and the imps and the lim imps, they have to exist, right? They're there, and they're measurable functions. The limit may not exist. If it does exist, it's also a measurable function. So, all right, I half lied. I'm going to prove it, but I'm going to just sketch the proof and not fill in all the details. So we'll call this a proof sketch. We'll at least do it for soup. So I'm going to say in set notation. Using set notation, right, we can consider the set of x such that the soup of f of I is less than or equal to t. And hey, what do you know? We're already using that blue box that I highlighted up here, right? We're going to try to show that the sets in the blue box here are measurable sets. So we're already getting some use out of that blue box. I told you. Remember the blue box. Anyway, if I consider this supremum, what is this set? Well, this set can actually be written as a countable intersection, we'll say 1 to infinity, of x such that fi of x is less than or equal to t. Why is that the case? Well, let's just stare at it for a second, right? The thing on the left is telling me that it's the set of x's such that the biggest fi could possibly be at x is still going to be less than t. That only occurs if for every I, fi of x is less than or equal to t. And so on. So this is why we can write in some sense, a supremum is kind of like an infinite intersection. A countable supremum is a countable intersection here. And these things are measurable sets, i.e. they exist in the point is they're elements of the sigma field X. So they're measurable. And what that means is that a countable intersection of measurable sets is measurable, right? Because of the properties of the sigma field, I'm allowed to take countable unions, of course, and then using complements and whatnot, I think. I have to remember exactly. I always get those complements and set subtractions and everything messed up. But anyway, using the properties of that a sigma field is closed under countable unions. It's also closed under countable intersections. De Morgan's laws. That's what I was thinking of. Anyway, it's closed under countable intersections. So that means that if I have a whole bunch of sets, I can take a countable intersection. That means this set defined by the sup is measurable for any t. Those sets define the Borel sigma field. So we're done, right? We know that the sup of a countable collection of FIs is in fact measurable if, of course, all of those FIs are measurable. So this is for sup. For inf, do the same thing, noting that, well, let's write that out so it's clear, right? I mean, you can kind of take a guess that if the sup is an intersection, the inf is probably going to be the opposite, which is an infinite union. But nevertheless, right, if we take the infimum, now we're saying something different. We're no longer saying all of the functions have to be less than t. We just are saying there exists at least one I such that fi of x is less than or equal to t. So it's an infinite union, a countably infinite union of measurable sets. Therefore, it's measurable. Therefore, we're done. Let's see. Oh, yeah. And let's say, okay, well, wait, well, how do we do lim sup over I of fi? Well, in this case, we can write the lim sup. I mean, not in this case, in any case, in every case of lim sups, we can write that as the infimum of the supremum j greater than or equal to I of fi. So the lim sup is an inf of a sup of the fi's, and as a result, you can just basically do what we did above, but twice. If f is measurable, then the sup of f is measurable, and therefore the inf of the sup of f is also measurable. I feel like I'm going to break out in a Gilbert and Sullivan song, and then the inf of the sup of the f of the sup of the f and the inf and the drives you crazy, right? All this stuff. Anyway, the same thing occurs in this case. We just switch the roles of inf and sup. This should be fj to be precise. Yeah, I got that backward. I did a typo there, I think, in my notes. The point is that we're taking for let's say we fix I, we're taking the infimum of all the j's greater than I, and then we're taking the sup over all of that. And right, if you have a smaller collection of things, if the set of things you're suping or you're infing over gets smaller, it's only going to get bigger, and therefore this is equivalent to saying I going to infinity. It's basically going to push I to infinity. So we're looking at kind of the sup and the inf in the limiting sense. Oh yeah, and lastly, we didn't do lim yet. Lastly, if the limit of fi exists, it may not. If it does, then we have that the lim sup of the fi is equal to the lim of the fi is equal to the lim inf of the fi. They're all equal to each other, so then we're done, right? If it doesn't exist, well, then the lim sup and the lim inf are not equal to each other. They're still measurable, but the limit doesn't exist, so it can't be measurable. Right. Cool fact number 5. I'll give myself a little QED box for that one, just because we did kind of prove it. I kind of sketched through the last little bits pretty fast, but I think you see the idea of where we're going here. Oh yeah, here, this is a good one, because it just gets into all the crazy math definitions. And it's really a one-line thing. Let f map x to R be continuous. Then it is measurable. I guess strictly speaking, we're always just saying Borel measurable here. Every time I say measurable and the without being more precise, and the output space is like the reals, or say like the positive reals or something, or even the unit interval, then we're just going to assume that that means it's measurable with respect to the Borel sigma field. Anyway, why is that true? Well, it's kind of a one-line proof, but the proof is not so interesting. The point is it's the definition of what it means to be continuous, right? I mean, when you do Calc 1 or something, you talk about a continuous function, and it's like, oh, well, if I don't pick up my pencil, then it's continuous, right? What in the world does it mean to be continuous if we're mapping from some space x into the reals? Well, the point is that, did I leave it? Yeah. A function between two topological spaces. Remember, when I say topological spaces, I just mean a space with some open sets and another space with other open sets. Is said to be continuous Man, I cannot spell when I do math. Continuous if the inverse image of an open set is open. Okay, so what that means, i.e. in this context, if U, a subset of the real line, is open, then necessarily F inverse of U is open in X. Right, so what we're saying is that the inverse image of an open set has to be an open set. So if I take an open set in R, the inverse image is an open set in X. Therefore, F inverse of U is measurable. I guess in this case we're assuming the Borel sigma. Okay, measurable. Maybe we'll just, to be really precise here, because yeah, okay, I didn't say what measurability. We'll say Borel measurable. So we're mapping, Borel sigma field into Borel sigma field in some sense, or inverse mapping Borel sigma field into Borel sigma field. Because otherwise you could define a really dumb sigma algebra or sigma field or sigma algebra X on X, right? And then it wouldn't actually work. But here we're assuming this is what we want, right? Anyway, the point is that if I take an open, basically since F inverse of U is open, it's in the Borel sigma field B of X, and thus it has to be measurable. Now, secondly, that's part one. Since the open sets generate B of, we'll say, X, the Borel sets on X, we're done, right? We get that F is measurable. Now, strictly speaking, right, we'll give myself a little QED box. The sigma field, the Borel sets on X, could possibly be a bigger collection than the Borel sets on R. It can't be the other way around, or else we can't have continuous, like the idea of a continuous function. Well, would a continuous function still work in that case? I feel like that wouldn't, no, because it wouldn't be measurable. That wouldn't make sense. What I'm getting at here is that note that the sigma field that's generated by the collection of F inverse U such that U is a subset of the reals and open, is contained. It may equal the Borel sets on X, but it could be contained in them as well. So that's what I was trying to get at, is the fact that we have all these open sets on the real line. Each of those is going to be mapped back into an open set on X. If I take all of those open sets on X that were generated from F inverse, I can get a sigma field out of that. That sigma field is going to be contained within the Borel sigma field. It could be the Borel sigma field, but it could also be smaller than it as well, depending on what X is. And maybe we can come up with some example. I don't have one off the top of my head, so I'm not going to speculate on one right now. Ah, yes, and this rant that I'm on here leads into our final cool fact, number 6, which is given a collection of functions fi mapping x into y, we can make them measurable. I'll say make them, with the emphasis on make them measurable. By constructing a measurable space x script x where sigma of the collection of fi, let's say I in, did I give it an index? I guess I didn't. I in I is contained in x. Where, just to be clear, this is the sigma field constructed from the sets fi inverse b for all I and for all b in y. So what that means is that if I have a bunch of functions that map from x to y, and I take all of the sets that live in the sigma field y script y, and I map them back into x for all I, now I have a big collection of sets that just got mapped into x. If I take those sets and I generate a sigma field from it, I can now define, make these functions all measurable with respect to that sigma field, or any sigma field x that is that contains this sigma field. We could make it bigger, right? We could just start throwing in other sets that have nothing to do with anything. That's not going to break it, but we have to make sure that we have all of these fi sets, these fi inverse sets, that is, and the sigma field generated by those fi inverse sets. And then we have measurable functions. Cool. So that means that if we have functions that aren't measurable, or we could always try to make them measurable, I guess. Though strictly speaking, oftentimes we'll just be working with like Borel functions, so like Borel to Borel, or like Lebesgue functions, Lebesgue measurable functions, and then we'll just have to say, well, is this Lebesgue measurable or is it not, and things like that. Right. Well, we're almost done, but I have a couple definitions I want to mention just quickly before we end for today. All right, so before we end for today, I do want to just mention a couple definitions. The first is the idea of almost everywhere versus almost surely. So let omega f mu be a measure space. Then for f and g, which map from omega into the reals, we say that f is equal to g a e, which is almost everywhere equal, when the set n equal to the x such that f of x is not equal to g of x, well, what? It's going to have measure 0, right? That's the notation n is kind of telling you it's going to be a null set, a mu null set. So it means that f and x f and g are equal almost everywhere. The only parts where they're not equal is on some negligible set of measure 0. And in probability theory and statistics and related fields, we basically often say, we say AS for almost surely, or you'll sometimes see authors use WP1 for with probability 1. They're all the same thing, but it is worth just noting that different authors will use different terminology. If you're dealing with people talking about analysis, they're probably going to say almost everywhere. If you read a probability or a stats paper, they're probably going to say almost surely. But yeah, there's no real difference there. Oh yes, and I have an example of two functions being equal almost everywhere. And this is the most classic example probably that you get whenever you take a measure theory course, which is let the unit interval, I guess I could do half open, doesn't really matter in this case, right? The unit interval, the Borel sets, and Lebesgue measure. I'll just do half open just to keep with what we've been doing this whole time. Let this thing, be a measure space. This is kind of the standard one we'd work with. Lebesgue measure, Borel sets, unit interval. All right, this is good stuff. Furthermore, let f of t, am I using, yeah, I guess I'm using t. F of t is going to be 0 for all t in the unit interval. All right, so it's super boring. It's 0 everywhere. It's constant. On the other hand, let g of t equal 0 for all t on the unit interval minus the rational numbers. And maybe I'll do it like this, 0, and it's going to equal 1 for all t in that are rational numbers in this unit interval intersect with the rational numbers. Okay, so f is just 0 everywhere. G is in some sense impossible for me to draw. I guess it's not impossible. It's 1 and 0. So G is basically going to look like this. It's going to have two lines in some sense because of the density of the rationals. If this is 0 and this is 1. So if I'm at a rational number, I get a value of 1. If I'm at an irrational number, I get a value of 0. The claim is that f is equal to g almost everywhere, almost surely, almost whatever. So that is the Lebesgue measure of the rational numbers on the unit interval. I mean, the rational numbers in general, but the rational numbers in this case contained within the unit interval is equal to 0. So that's the claim, is that this should be 0. Why is that true? Well, we could actually just show in general we could actually show that the Lebesgue measure of the entire collection of rational numbers is equal to 0. This is over the entire real line. How do you do that? Well, I'll leave that as something for you to try, but I'll push you in the right direction. And here's what we can do. Try enumerating Qm m from 1 to infinity to be the rational numbers. In this case, I guess we're taking for granted that the rational numbers are countable, but yes, okay, the rational numbers are countably infinite. That means I can put them into a one-to-one correspondence with the natural numbers, which means I can index them. I can start with, like, the first rational number, and I can go up from there, right, to infinity, and I can go through all of them. Now, try enumerating the rational numbers and surrounding each by an interval of the form Qm minus epsilon 2 to the minus m minus 1, Qm plus epsilon 2 to the minus m minus 1. For any epsilon greater than 0. So what we're doing, right, is we're going to each rational number and we're giving it a little tiny interval around it. For some epsilon greater than 0, we're giving it a tiny interval, but we're also taking this 2 to the minus m minus 1, which means these intervals are going to start to get smaller as we go further out into the rationals. Basically, compute this thing and take epsilon to 0 to show that the Lebesgue measure, in this case, of the rationals will in fact be 0. And in fact, this argument will hold for any countably infinite collection of points. If you want to have a positive Lebesgue measure, you're going to need an uncountable infinity. Not necessarily, or not necessarily, it's not a sufficient condition, because I'm pretty sure that's the Cantor set, right? I need to double check that, but I'm pretty sure the Cantor set has Lebesgue measure 0, but is uncountably infinite. Though I will double check that just to make sure I'm not misremembering my facts. But yeah, with that is everything I wanted to cover about measurable functions. This is going to be important because it's going to lead us right into the next couple lectures, which is going to be about integration. We want to be able to take an integral of a measurable function, and this is going to similarly, in a probability sense, be looking at expectations of measurable random variables and other things we might be interested in that context. There's a lot of really cool theorems coming up, but before we get to those cool theorems, we're going to have to define an integral in a more proper sense, and we'll be doing that in the next video lecture, so stay tuned for that one.